So today we're going to start talking about the last chapter that we're going to cover in this class. It's chapter 7, Parametric Equations and Polar Coordinates. Today we're going to start talking about section 7.1, which is parametric equation. Now the reason why parametric equations are useful is because we use them to describe curves that are not necessarily functions. So if we have a parameter that's independent on x and independent, but like x and y depend on it, as the parameter increases, the values of x and y will trace a curve or like a path along our plane. So for example, if the most common parameter that we use is t, which is the time. So if x and y are functions of time, we can describe a position using any point x of t, y of t in the plane for a given object that moves along a curved path. So these equations are very useful in applied mathematics. So let's define parametric equations. So if we have two functions that are continuous, x and y, so they're continuous in terms of the variable t on a certain interval I, the equation x equals x of t, y equals y of t are called parametric equations, and t is my parameter. So now here you have to be careful. When I say x and y here, they represent functions. They have equations. Now the graph of parametric equations, we can either call it a parametric curve or a plane curve. So let's see how we're gonna deal with these equations. So the first thing that we're gonna learn is how to sketch a set of parametric equations. So for example, if I have x of t is equal to t squared minus 3, y of t is equal to 2t plus 1, and I have the interval between negative 2 and 3. So to graph the curve, what we need to do, we set up a table. I write different variables, different values of t, then I find the values of x of t and y of t that corresponds to that, and then we just plot points and connect the curve. So for example here, I'm going to take all whole numbers between negative 2 and 3. So if you have negative 2, once you plug it into your x, you're going to get 1. Once you plug in negative 2, you're going to get negative 2. Then just keep plugging values of t into your x of t. So you're going to get negative 3, negative 2, 1, and 6. Then similarly for y of t, you just plug in values of t here. Negative 3, negative 1, 1, 3, 5, and 7. Now once you're done with finding the values, you want to create points. So all of the points are going to be of the form x of t, y of t. So you're going to have the following points. 1, negative 3. So 1, negative 3, negative 2, negative 1, negative 3, 1, negative 2, 3, 1, 5, and 6, 7. Now obviously you don't need all of these points. You can plot 3, 4 points and that would be enough. So now if you look at the graph, I already graphed it. Here we have 1, negative 3 at time equals negative 2. Then if you look here, negative 3, 1 is at time 0. Similarly, you can plot the rest of the points, and as you can see, as time or as our parameter is increasing from negative 2 to 3, the values of x are moving along, x and y, are moving along the curve. Okay, perfect. So that's the first thing that you need to know. If you have a set of parametric equations, how can I sketch the graph of these equations? You just set up a table, find the points, and then plot them on the plane. That's it. Now, if the second thing that we need to learn is how we want to eliminate the parameter that we have. So sometimes to better understand the curve of parametric equations, we can rewrite the equations as a single equation. So we want to relate x and y together and get only one equation. So if we have like an equation in terms of like y equals something in terms of x, it's just a regular function that we already know some properties of, and we can easily just like graph or like know whether it's like increasing, decreasing, and so on. So to eliminate the parameter, we solve either the equations, like we solve either the x of t or the y of t in terms of t, and then once you get the value of t, you plug it into the other equation. So let's try it for a. If I have x of t is radical 2t plus 4, y of t is 2t plus 1, so let's solve x of t, for example. So I have x is equal to 2t plus 4. If you want to solve it for t, you just square both sides, 2t plus 4, then t is going to be equal x squared minus 4 over 2. And now here x is definitely bigger than or equal to 0. So now if we substitute back into your y of t, so instead of t, you plug in this equation, we're going to get 2 times x squared minus 4 over 2 plus 1. If you simplify the 2 with the 2, you're going to get x squared minus 3. Now the only thing left is I want to get the values of x. So I have a function that's equal to y equals x squared minus 3, and I have an interval in terms of x. So let's substitute the endpoints. When t is negative 2, if you plug it here, you're going to get 0. Similarly, when t is 6, once you plug it there, you're going to get x equals 4. So this is the equation that we got and the interval after eliminating the parameter that we have. So once you graph it, you're going to get this graph right here. Okay, now for the second example, although the eliminating the parameter, like the first thing that I said was like, oh, let's solve one of the equations in terms of t and so on. When you have sine and cosine, that's kind of difficult because sine and cosines are not one-to-one. So if they're not one-to-one, I'm not going to be able to find the inverse. So I'm not going to be able to solve the equation in terms of t. So what we do here, we rewrite the equations that we have, and we use one of the identities to help us find the equation in terms of x and y. So here, once you solve it for cosine of t and sine of t, you're going to get this. And then I'm going to use the identity that we already know, which is cosine squared plus sine squared is equal to 1. So let's just plug the values in. So you're going to have x over 4 squared plus y over 3 squared, and that's equal to 1. Then you're going to get x squared over 16 plus y squared over 9 equals to 1. And this is an equation of an ellipse. So it's a horizontal ellipse with the values of x, 4, and negative 4, because you take the square root of 16. And then the values of y is 3 and negative 3, because you take the square root of 9. And if you go back to your t value, it's between 0 and 2 pi. So you're moving anti-clockwise along your ellipse for different values of t. So these are the two main ideas of eliminating the parameter. You either solve the equation for t, substitute in the other equation, or you use some identities that you already know if you have sine and cosine. Now the last thing that we're going to talk about today, if I want to parameterize a curve. So here, what happens is I start with an equation of a curve, and I want to find parametric equations for that curve. So keep in mind that we can always parameterize a curve by defining my x of t to be equal to t. Then you plug in t into your function y. So that way you get a parametric equation for that curve. So for example, let's find two different pairs of parametric equation to represent this graph. So I started with a regular graph that we already know, y equals something in terms of x, and I want to parameterize that to get parametric equations in terms of t. So I want to get x of t and y of t. So the easiest thing that we already know, that if I start with x of t is equal to t, that would be one set of equations. So now you just plug in t instead of x, and you're going to get your y of t. So here we don't have any restrictions onto this function, so we're not going to have any restrictions on RT. Now to find another set of parametric equations, we have the freedom of choice of x of t. So we can choose any value of t as long as there is no restrictions on on Rx. So here I don't have any restrictions, so I can use any value of x. So for example, here I took x of t is equal to 2t minus 1. Any equation, that's okay. Once you set the value of x of t, you just take it and you plug it into your original equation that we have. So now I have 2t minus 1 squared minus 3. So you're going to get 4t squared minus 4t plus 1 minus 3. Once you simplify, you're going to get this equation. So now we were able to find two sets of parametric equations for the function that we started with. So now I have t and then 2t squared minus 3, or 2t minus 1 and 8t squared minus 8t minus 1. And you can find many more parameterization just by changing the value of x of t that you start with and then just plug it into your y of t. So that would be it for the first section of this chapter. If you have any questions, please let me know, and you can do some extra practice problems if you want.